Hello and welcome to Train Signal. You are watching a lesson about the Linux boot process. We began our study delving into the inner workings of your Linux system's hardware settings. It may have seemed like an unusual place to start, but this critical information will serve as a much-needed building block upon which our future lessons are based. Throughout this course, you'll find that our subject matter will fit neatly into one of two categories: hardware or software. One cannot function without the other, so as an administrator or user, your time, whether it's installation, troubleshooting, or just general systems maintenance, will fall into one of these two camps. Along these lines, one of the most important concepts is to understand how the Linux operating system boots up. This is one of those instances where Linux is decidedly different from Windows. The first Linux distribution that I tried was Mandrake, and that's known today as Mandriva. Now, coming from the Windows graphical environment at the time, those unrecognizable characters and driver names that scrolled across the screen looked pretty much like a foreign language to me. But today, most distributions do a good job of hiding those messages. But there are some gems in those messages that may prove quite helpful when trying to troubleshoot issues with your computer. So in this lesson, we'll start with a look at the Linux BIOS. That's the program that initiates the boot process when you power on your system. We'll continue with the bootloader, which essentially takes a handoff from the BIOS and continues along with the boot process. Then we'll move on to the boot sequence, the steps that are performed during the boot process. Next, to view those boot messages I mentioned, we'll take a look at the kernel ring buffer and log file boot events. First up, the BIOS. We touched on the BIOS just a bit in our previous lesson, but now it's our chance to dig just a little bit deeper. The BIOS, or Basic Input-Output System, is located on your computer's motherboard in ROM or flash memory. No matter which operating system you use, the BIOS always kicks off the boot process. When you turn on the computer, the BIOS springs into action. First, it performs a power-on self-test, or POST, which tests system components to make sure that they're functioning properly. I think at one time or another, most of us have booted our system to a rather nasty-looking error message or a series of indignant beeps. That's why boot failures at this stage usually point to a hardware problem. Next, the BIOS initializes hardware, then loads the bootloader from whatever boot device is indicated. This is usually the first hard disk. And finally, it hands off control to the bootloader that proceeds with loading the operating system. What you see here on the screen is a typical BIOS configuration screen, but yours may look a little different depending on your system. You access the BIOS's configuration utility typically by hitting a function key like F1 or F2 just as your system is booting. And if you recall from our first lesson, this information is going to be displayed at the bottom of your screen during the boot process. What's important to note here on the screen is that you can enable and disable system hardware. Things like Ethernet and USB ports and video hardware, and probably even hard disk controllers, can all be configured from within the BIOS. And when might you want to disable this hardware? Perhaps for testing purposes, or if you choose to use a plug-in card like a video card. Now, depending on your hardware, how you change these settings will be different, but on-screen prompts and help will guide you through the process. You have to hit another function key, typically F10, to save your changes, exit, and reboot your system. After the BIOS performs its tasks, it can confidently hand off control to someone else. Let's move on to the next phase, the bootloader. The BIOS has done its duty. Now it's resting comfortably until the next time that it's called on. The bootloader can take over. But first, the BIOS needs to know where to find it. The master boot record, or MBR, sits in the boot sector of your hard drive and contains both the MBR partition table, which we'll talk about later, and the bootloader. Now, the bootloader's job is really important. It allows the CPU to access the hard disk and loads the operating system, or kernel, into memory. During Linux installation, a bootloader is usually configured automatically, but chances are you'll need to modify this configuration, particularly if you want to set up a system that will dual boot with another operating system like Windows or even another distribution of Linux. There are actually several different bootloaders, but for the purposes of the Linux Plus certification exam, there are only two that you need to focus on. The first is the Grand Unified Bootloader, also known as GRUB, and the second is the older, less used Linux loader, affectionately called Lilo. For now, we just need to understand the bootloader's role in the boot process. We'll cover the specific configuration concepts for each in a later lesson. The image you see on the screen is of the GRUB bootloader with a nice splash screen applied. The screen lists different Linux versions or kernels and gives you the option to select which one you'd like to boot. Both Lilo and GRUB can actually be loaded in the boot sector of a boot partition in addition to the MBR. If you're like me and still have a need to keep Windows on a separate partition and dual boot it with Linux, you have the option of keeping Windows as your primary bootloader and then directing it to boot your Linux kernel from a boot sector instead of the MBR. And since Windows has an ugly tendency to write its own MBR bootloader when it's installed, this is an often used option. In fact, my first thoroughly terrifying crash course in bootloader configuration was due to Windows overriding the Linux MBR bootloader. Remember that incredibly helpful Linux community that I mentioned before? It was only with their help that I was able to use a utility that we'll talk about later to set my Linux partition as the primary boot partition again. Next, let's take a look at all the steps involved in the boot sequence. From what we've covered so far, we know that the process of booting a Linux system has a number of stages. Once you power on your system, the BIOS does its part and then does a handoff to the bootloader. But what happens from there? At this point, regardless of the hardware, the process is actually pretty similar. Once the kernel is loaded, it has a series of tasks it must perform. It initializes devices, mounts the root partition, and then loading and executing your system's initial program. This is typically /sbin/init, but can vary depending on your distribution. sbin is another Linux system directory that we'll cover in a later lesson. Init gets a process ID of 1. A process ID is exactly what it sounds like, a number assigned to the process or programs running on your system. Init reads a file called init-tab to figure out what other programs it needs to run. The types of programs handled by init-tab include Getty programs that manage console logins, scripts for mounting other partitions or startup services, and an X-Display Manager, which provides for graphical login. Inevitably, things sometimes go awry, and the boot process is no exception. Remember those messages that scroll by the screen, often too quickly for you to gain any useful information from them? Luckily, that information is captured in a log file. Let's move on and examine the contents of the kernel ring buffer. The unthinkable has happened. Your system has failed to boot. You're not sure whether the problem is related to your hardware or to that new video card driver you just installed. Instead of wringing your hands in exasperation, you can tap into the clues in the form of the kernel and module log information left for you in the kernel ring buffer. You can access this information with one deceptively simple command, dmesg. The image on the screen displays the output of this command, but let's go back to our Linux terminal window and give it a try on a live system. Again, from the Applications menu, and I'm using Fedora 13, click on System and Terminal. From the command prompt, let's type in dmesg and hit Enter. As you can see, quite a bit of information scrolls by, and while you could use your arrow keys to scroll up, you can also use the less command and the pipe to page through your content. The pipe lets you direct output from one process to become the input of another, and on your keyboard, this is the key directly above your enter key to share space with the backslash. We'll cover both of these commands in more detail in a later session. This time, let's try typing in dmesg space pipe space less. As you can see, we have one page of content displayed. Now we can use our arrow keys to navigate the output. You can also search, for instance, for a particular piece of hardware by hitting the /. For the purposes of the certification exam, you don't need to be able to interpret any of this data, but you will need to know how to access it and how to navigate it. As you begin to hone your troubleshooting skills, you'll begin to recognize hardware names or types and chipsets and be able to use those to find messages related to certain devices in the output. For example, let's search for the term SCSI. Let's hit the / key and type in SCSI and hit enter. As you can see, the system comes back with information about the SCSI devices on our computer. The kernel ring buffer isn't the only place to find log information though. Next, we'll take a look at the system logger. During my own exploration of Linux, one of the best, but still one of the most frustrating features of the OS was that there was often more than one way to do any given task. I've personally witnessed merciless debates in the various Linux forums about the best way to do something, or the best program to use, the best distribution, or even things like pronunciation. My SATA may very well be someone else's SATA. The good thing is, the more time you spend with Linux, you'll develop your own best practices and shortcuts and the like. And you shouldn't be afraid to share those with the community. Just be forewarned that a healthy debate may ensue. So we've seen how to access log information in the kernel ring buffer. But another information source is the system logger or syslog-d. You should probably start your information quest in the /var/log/messages file. var is again another Linux system directory that we'll cover in depth in a later lesson. Other handy locations in the var directory might include syslog or just log itself. Let's take a look at the var log messages file. Back at our terminal window, let's clear the window from our previous output by typing clear. Now this command may be different depending on your distribution, so you may need to consult your documentation. If we hit enter, that clears. Now you'll need to gain root privileges to access the log files, so I'm going to use the su command to gain root privileges. We type in su and hit enter. It'll ask for password. You enter your password, and you can see that the prompt has changed with the word root in front. Now let's type in the cat command, cat, /var/log/messages. A common mistake is to forget to type in the leading slash, so if you receive an error, just be sure to make sure that slash is there. Let's hit enter. And again, we've got quite a bit of information, and it will take you some time to be able to decipher all of this, but for now it's important to know just how to access it. So we've taken a look at the var log messages file. Now let's switch over to Ubuntu to take a look at some more log files. To access the terminal, it's just a little bit different from Fedora. Click on Applications, then Accessories, and then Terminal. Now to view the contents of var log, we need to type in cd for change directory space /var/log. And we'll hit enter. Now let's type in the ls command, which will display the contents of the current directory. Type in ls and hit enter. Now if we scroll through this list, we'll see that there are actually several different log files, some for our applications, as you see here with ClamAV, and also with AppArmor. But what we're interested in here is the syslog file, which contains system log messages. So at the prompt, let's type in again the cat command, which will display the contents of a file. So it'll be cat space syslog. and hit enter. And what scrolls past on the screen is the entire contents of this file. And again, you'll probably most likely use this information for troubleshooting purposes. Okay, let's head back over to the presentation. Inevitably, it'll happen. You'll turn on your system and it'll stubbornly refuse to boot up at all. You won't know if the offender is an aging hard disk or if it's that new video driver you installed. But if your system doesn't boot, the kernel ring will display messages on screen. Unfortunately, in many distributions, this information is hidden, but pressing the escape key during the boot process will sometimes allow them to be viewed, and you can begin your troubleshooting from there. For those of you pursuing certification, concentrate on log file locations, how to display them, and how to navigate them. This wraps up this lesson on the Linux boot process. Let's review what we've covered. Well, with another Linux lesson under your belt, I hope both your interest and confidence level in your decision to explore Linux are growing. It gets better. In this lesson, we covered the Linux BIOS and how it fits into the boot process when you turn on your computer. And then the handoff to the bootloader, which continues the boot process. Then we moved on to the boot sequence, the steps that are performed during the boot process. Next, to help troubleshoot boot problems, we reviewed how to access the kernel ring buffer and log file boot events. Each of the concepts covered in this lesson are useful for troubleshooting, and those pursuing certification should again spend some time practicing commands, thoroughly committing the processes to memory, and perusing your log files. It's good to understand how things look when they're working properly, as it'll make it easier to spot issues when something goes wrong. Thank you for watching, and I'll see you in the next lesson.